Hi class, we are starting chapter 4.2, which is basis and dimension. This is a really abstract section as well, much more so than the previous section. However, the topic is very, very important, and again, we'll lay the groundwork for pretty much everything we're going to do in the class, right? So, we've actually alluded to this idea of a basis many times over the last three chapters, I should say. Chapters 2, chapters 3, and chapters 5, actually. So we're going to talk more about basis. We're just going to put a name to the sort of things that I've been stressing a lot in this class. Common ideas that we've been going over, right? So, a set B, okay, this is a fancy B because this is a fancy set. So a set of vectors, U1, U2, so forth, all the way up until UN, of vectors is called a basis for a subspace, right? So it has to be a subspace if one, right, A, B spans F, S, okay? And part B is that B is a linearly independent set, okay? A linearly independent spanning set of a subspace S is a basis for that subspace S, okay? We've been talking a lot about the relationship between spanning sets, linear independence, and linear combinations, okay? A spanning set that is linearly independent is what we call a basis, right? So we call it a linearly independent spanning set, okay? So that is what a basis is. A basis is basically a set of vectors that allow you to generate a complete space. That's pretty much what it is, right? So it's a spanning set, and those set of vectors are linearly independent. So let's look at an example, okay? Let's look at the set of vectors 1, 0 and 0, 1. We've referenced these several times. These are the unit vectors, the standard vectors for R2. They are called the basis for R2, okay? So these two vectors forms a basis for R2 since any vector in R2 can be generated by these two vectors, and it's very clear that these two vectors are also linearly independent. So this set B is your basis, okay? In fact, it's called the standard basis, okay? Because it's your basic X and Y axes vectors, okay? So I have two linearly independent vectors in R2, so the set of vectors span R2. When we were talking about linear independence and span, I said this many times as a way to check that something spans your space or not, right? I said if you want to span R3, you are going to need three vectors that are all linearly independent and all have 3 elements each. You are guaranteed that if you have 3 of them in R3 and they're all linearly independent, that they span R3 itself, okay? And so if I had 4 vectors in R3, only 3 of them can be linearly independent. So even if I have 4, yes, it will span R3, but they would not be linearly independent, so they would not be a basis, okay? So a basis is the minimum number of vectors that you need in order to span a space, okay? You can think of it in that sense as well. So the set of vectors 1, 1 and 2, negative 1 is also a basis for R2 because I have 2 vectors in R2, and these 2 vectors are linearly independent. I can tell they're linearly independent because they are not constant multiples of each other, right? Because there's only 2. The only way for one of these to be a linear combination of the other is if one of these is a constant multiple of the other, because there's only 2 of them, right? So again, here we go to my favorite way of checking things. Another way to check whether a set of vectors forms a basis or not is to turn these vectors into a matrix and take the determinant of that matrix. If the determinant is 0, it cannot be a basis, right? Because remember, we had that big theorem at the very end of the last video. The large theorem said we had all these equivalencies, and one was that if your determinant is not 0, then your set of vectors are linearly independent they are a spanning set. As a linear transformation, they are onto, they are one-to-one. We had a whole list of things. If I turn this into a matrix, then this is invertible, right? There's a lot of things that we can do if we know that the determinant of A is non-zero, right? So that's the easiest check. So the determinant of A equals 0 implies that A would be singular or linearly dependent, and thus would not span R2 nor be a linearly independent set. Okay. So theorem. If B is a set of vectors u1, u2 up to um is a basis for a subspace that we call S, then for every vector S inside of this subspace S, there is a unique set of constants, okay? A unique set of constants, because they're in R, such that S can be written as a linear combination of those constants. So this also comes from the big theorem that we had, where we said that every vector B has a unique solution for the matrix equation AX equals B. It's basically us saying the same thing. It says every vector in my subspace that is formed by this set of vectors, this basis set, okay, has a unique representation. That means there's no way for me to form it in more than one way. What this is basically saying, this comes from the idea of being linearly independent, okay? Because remember, when you're linearly dependent, there's an infinite number of ways to represent a vector. You have infinite solutions for something. So here what we're saying is that a single vector S has a single unique representation in terms of a linear combination of these basis vectors, okay? So the basis for the subspace can form any vector in that subspace with a unique linear combination of the basis vectors themselves. Very, very important theorem here, okay? So each vector in S has a unique linear combination representation consisting of the basis vectors of S, right? So just me putting it on paper in your write-up so you can look at it later, right? Theorem. Say that we have two matrices, okay? They're n by m with row value entries, and A and B are equivalent, meaning that if I do row operations on A, I will get to B, okay? That's what I mean by equivalent, okay? Then a subspace of Rm, and again, this should be the fancy R, okay, not a regular R, but it doesn't matter. So a subspace of Rm spanned by the rows of A is the same subspace that is spanned by the rows of B. Okay, so the rows of A, okay, the subspace created by the row vectors of A is the same space that the row vectors of B can also create, as long as A and B are equivalent, meaning if I reduce A down to B using row operations, the row vectors span the same space, okay? The rows, we're talking about rows here, not columns, okay? So these rows is what we call the row space, okay? So the row space of A is equal to the row space of B if A and B are equivalent. So again, the space spanned by the rows of A is equal to the space spanned by the rows of B, okay? So here's an example. I have 4 vectors in R3. Obviously, this set of vectors is not a basis because I have one too many vectors, right? So it's not a basis because it is not going to be linearly independent. I have at least one too many vectors here, okay? So it is clear that B is not a linearly independent set of vectors since there are more than 3 vectors with 3 elements each, okay? So B is not a basis. So we want a basis for the subspace S generated by the span of B. So all the vectors that I can create with this set of vectors, I want to create a basis for, okay? Now, let's talk about how to do that. So what we want to do is we want to create a matrix whose rows consist of the basis vectors b. Okay, so we're going to turn these column vectors into row vectors because we're talking about row space here. So remember, even though these are column vector form right now, for what I need to do, I need to turn these into rows, okay, because we're talking about the row space of one matrix being equal to the row space of another. So these are going to be my rows of a matrix. So I'll have a 4 by 3 matrix. And I'm going to reduce that down to row echelon form. I do not need to go all the way to reduced row echelon form, just row echelon form, okay? The rows that contain pivot positions in my B vector will be the vectors of B, right, that span the same subspace S as this set of vectors, okay? So what am I talking about? So I'm going to make a matrix A. My previous set of vectors that look like column vectors, I'm going to write those as row vectors, okay? And now that I have row vectors, I can reduce these down, okay? So it's very clear here that this row and this row are the only rows that have pivot positions. So that means that this vector and this row vector spans the exact same space that each of these row vectors span, okay? So 1, 5, 4, 3, 2, and 0, 1, 2 forms a basis for the subspace S that is generated by this entire set of vectors here, okay? So this entire set of vectors can be generated by these two vectors. So again, these two vectors, these two rows, span the exact same space that all of these rows span, okay? So now, we were able to create a basis for our subspace. But the big question you should be asking yourself is, why can't I just use some of the vectors that I already have, right? How can I create the same space but using the same vectors I currently have instead of making brand new vectors? So let's talk about this, okay? Before we do that, notice that I can multiply either of these by a scalar multiple, and it'll still span the same space. So if I want to, I can clear these denominators out by multiplying everything by 4, and I get 4, 5, and then this will turn into 6. So these two set of vectors actually span the same set also, okay? So a constant multiple of the first basis vector where we clear the denominators. We can also do reduced row echelon form if we wanted to, and that will do the exact same thing for finding a basis, okay? So if I were to have taken this and reduced it all the way down, take this all the way down to the reduced row echelon form, these two vectors span the exact same space that these span, and that all of these span as well. So there's several ways for us to find our basis, right? Right, so these two row vectors, 1, 0, -1, 0, 1, 2, they span the same space that these two row vectors span here, and they all span the same space that this entire space spans or generates, okay? So again, as I alluded to before, it would be nice to be able to make a basis out of the vectors that we have already, right? So the real question is, how can I do this with the vectors I have already, okay? Meaning that, remember that I said a basis is the minimum number of vectors that we need in order to span a space. Obviously, I only need 2, okay? So here I had 2, here I had 2, here I had 2. I have 4 originally, so my question becomes, which 2 of these can I get rid of in order to span the same space? So really what's happening here is, let's say I did throw this into a matrix, a 3 by 4 matrix, I would end up having basically 2 free variables here, okay? So what 2 vectors can I throw away so that I have my 2 vectors that work for a basis from my original set, rather than making up brand new ones that span the same space. It's nice to know that they all span the same space, but what about the ones that I have already, right? So which ones can I throw away and which ones should I keep from my original set B? So we need a linearly independent spanning set. So we would need at most 3 vectors if the span of B equaled R3, but we can tell here that it does not because we do not have 3 for all of my other basis sets that I found, right? It doesn't. We had 2 vectors in R3 that formed the basis for S in our previous exploration, those last 2 or 3 cases. So my subspace that I have that's spanned by B is not equal to all of R3, okay? So what 2 vectors of B do we need, and which 2 can we discard so that we have a linearly independent set? Again, this is just reiterating what I just said, right? So what we're going to do is we're going to make a matrix A of the column vectors of B and reduce that to reduced row echelon form, okay? So here the columns that have pivot positions will correspond to the vectors that I have in B that will be linearly independent spanning set of the vectors for my subspace S. So what the hell am I saying? What we're going to do is we're going to take these vectors of B, okay? We're going to turn these into column vectors, okay, as they are, and we're going to make it into a matrix. We're going to do reduced row echelon form, and wherever I have pivot positions in my reduced row echelon form, those columns that have pivot positions are going to tell me which vectors I need from my original set B, okay? So if we want to create a basis out of brand new vectors that span the same space, then I turn these into row vectors and I do a row echelon form like I did here. And wherever there's a row with a pivot position, that's going to span the same space, okay? If I want to use my original vectors from my set, I create a matrix just like this where these are column vectors. I do the same thing. I do a row echelon form, and wherever I have ones in the pivot position, that's going to tell me which column vectors to choose from my original basis, okay? So let's go ahead and go here. So for B, we have, okay, we're going to turn this into a matrix as column vectors. We're going to reduce it down to row echelon form. And as you see, it's the first 2 columns here that have pivot positions. My 2 free variables are here. So that means that my first vector and my second vector from A are a basis. So 1, 2, 3, 4, 5, 6. Those 2 from B are what form a basis for the entire set. So whatever this entire set generates, these 2 sets generate as well. So these are my linearly independent vectors. Both of these vectors can be made by linear combinations of these 2 vectors. So these are my 2 spanning linearly independent vectors out of this entire set of vectors. And again, I did that by making it into column vectors and then reducing it down. And wherever the pivot positions were in the columns is how I choose my original vectors. Again, when I turn them into rows and I reduce it down, wherever my rows have pivots, those entire rows become a basis that forms the same space, but they are made from different vectors. To use the same vectors, I do pretty much the same thing, but in columns, okay? Therefore, the first 2 vectors of B form a basis for the space that's generated by that set of vectors B, okay? Therefore, 1, 2, 3, and 4, 5, 6 form a basis for my subspace S. So we could have put this matrix into REF to find the pivots instead of reduced row echelon if we wanted to, okay? So we didn't have to go all the way to reduced row echelon, but it's much cleaner and it's easier to find. Remember, reduced echelon form would have just had a number here and some different values, right? But I still would have had the pivot positions in the same columns. But reduced row echelon form makes it easy to see exactly where it is because everything in the column is 0 except for the single pivot position. So it's really up to you, but you could have used row echelon form as well. Okay. So let's go into a theorem. Okay. Say that U is a matrix formed by column vectors u1 through um. V is also a matrix formed by column vectors v1 through vm, and that U and V are equivalent matrices. Again, that means that V can be formed by doing row operations on U. Okay. If there exists a set of constants, right, a set of scalars, such that I write U as a linear combination with those scalars and I get out the 0 vector, then I can use those exact same scalar values to write a linear combination of the vectors of V to make the 0 vector as well. Okay. So equivalent matrices have the same null space. That's what this is saying, right? So remember what null space means? It means that if I have a unique set of vectors, set of coefficients that give me the 0 vector out, that's the things that send me to the null space, right? So it's basically saying that if I reduce one matrix down, they will have the same null space. Okay. So theorem, say I have a subspace of Rn, then every basis for this subspace has the same number of vectors. So I've said that a few times, but this is the first time you really see it in the theorem. Okay. And this number of vectors is called the dimension of S. And we know the dimension of S as dim of S. Okay, the dimension of S. Right. So again, notice for my previous example, I had 2 vectors to form the basis for that subspace. Right. Here I used the original column vectors. Okay. Here I used not the original column vectors. I made these vectors, but it was 2. Right. Here there was only 2. Here there was only 2. I kept saying there's only 2 here in order to form the basis, right? So the dimension of the space spanned by B has dimension 2 because I only need 2 vectors in order to create that subspace. Okay. So that's what that theorem is saying. All right. This first theorem here about the null spaces being equivalent, what it's basically saying is that the null space of A in this example and this null space are equivalent. Okay. So it's just a repeat of a previous theorem that we've seen actually, but a little bit more fleshed out, right? So the null space of A is equal to the null space of its reduced form. The null space of A is equivalent to its reduced form. These 2 null spaces are equivalent as well. Okay, they'll have the same null space. That should make sense. All right, so that was this theorem, and that was this theorem. Okay. So we notate that the dimension of Rn is always going to be equal to n, right? So the dimension of R3 is always 3, right? Because that's an entire space. It's a full space. It's what we call a vector space, right? So theorem. Say that U is a set of vectors, u1 through um, is a set of vectors in a subspace S. Okay. S not being equal to the set of vectors that is just a 0 vector. Okay. So if U is linearly independent, then either U is a basis for S, or I can add vectors to S to make it a basis, right? So if this is linearly independent, then it should be a basis for S. And if it's not a basis for S, meaning that I don't yet have enough vectors to generate all of S, there should be vectors that I could still add in order to form a basis for S. Okay. So maybe this is linearly independent, but not a spanning set yet. So I should be able to add more linearly independent vectors to this set to make it a spanning set, right? That's what A is saying here. Okay. Here, if U spans S, then either it's a basis for S, or there's too many vectors and I can take some out and I can make it a basis. Okay. So is a basis of vectors can be removed to form a basis for S. So this is called, actually it has a name, it's called the addition and subtraction theorem. Okay. So it's saying you can either add vectors to a set of vectors to make it a basis, or you can remove vectors from a basis, from a set of vectors to make it a basis. Okay. We say that the dimension of the null space of A is called the nullity of A. So remember, null of A is a space. Nullity is a dimension. Null of A is a space. Nullity of A is a value. Okay, it's how many vectors you need to create the null space. Okay, so this is a space. The null space of A is a space. If you're taking the dimension of a space, you're going to get out a value. So the nullity of A is a value. Okay, example. Let's take the previous example we had, where I had 1, 2, 3, 4, 5, 6, 1, 1, 1, 2, 1, 0. That was coming from way back here, from this example that I had, right? We'll just refer to this example quite often in our exploration, right? So I just come all the way back here. Okay, I reduced row echelon. Okay, we saw this already, right? These were the pivot positions. That's how I knew that the dimension of the basis that this space spans was 2. Okay, but notice again I have 2 free variables, right? So when I write my solution X, this is the general solution for the things that get sent to 0. Okay, I finished out the solution. I set it equal to 0. I solve it just like we've done many times. And now I have 2 free variables. I have 2 vectors. Okay, that means that everything that gets sent to the null space can be generated as a linear combination of these 2 vectors. So the nullity of A is 2, because I need these 2 vectors in here to generate any single one vector. Okay, so the null of A is these 2 vectors. Again, we've talked about this in the last video, right? So this is how you find the null space of A, and the dimension of the null space of A is how many vectors there are in there, right? So remember, this is all the vectors that can be created by the span of these 2, right? As a linear combination. There's 2 there. So the dimension of the null space of A is the dimension of X, right? Which is the nullity of A, which is 2. So notice that my dimension for my basis of S was 2. My nullity was 2. And if I add those 2 values together, the dimension of S plus the null space of S, basically, right? It adds up to how many vectors I have here. So 2 plus 2 is 4, right? So these 2 were the dimension. These 2 were for the null space. If I add those 2 together, it tells me how many columns I have, right? Note that since subspace S is generated by 2 vectors, right? The span of 1, 2, 3, and 4, 5, 6 equaled S. Okay, that was from our exploration here. Okay, that's coming from the 2 pivot positions was 1, 2, 3, 4, 5, 6. Right, the span of this creates my space. So the dimension of S was 2. Okay, also note that the dimension of S and the nullity of A are equal to the total number of column vectors of A. So again, just reiterating what I had said earlier. So the dimension of S plus the nullity of A will always equal the number of columns that you have for your matrix. Okay, that is always true, right? Or the number of vectors we had in B. So that's actually our theorem. Okay, a set of M vectors in a subspace of dimension M are linearly independent if and only if they span the subspace. Okay, so again, this has to do with a basis, right? If you have a spanning linearly independent set, okay, then you should have an M by M matrix. Okay, say S1 is a subspace of S2 and S2 is a subspace of Rn. Okay, then the dimension of S1 has to be less than or equal to the dimension of S2, because it's a subspace of S2, right? And S2 is a subspace of Rn. And the dimensions are equal if and only if those two subspaces are equivalent to each other, okay, or equal to each other. Next theorem. Say S is a subspace such that the dimension of S is K, right? So now we're referring to what's going on up here. And let U be a set of vectors, U1, U2 through UM, that is a set of vectors from S, that subspace we're in, okay? If M is less than K, so if the number of vectors I have is less than the dimension, okay, of S, so I have less vectors in U than there are basis vectors for S, then U does not span S, okay? If M is more than K, so I have more vectors in my set S than I do for the basis vectors for S, then I cannot be linearly independent, okay? So again, let's come all the way back to this example, right? Here, I only had two vectors that were a basis, right? But I had four vectors. So that means this set of vectors cannot be linearly independent, okay? That was part B. Come all the way back down here, okay? I had more vectors in my set than I did basis vectors. Okay, so they had to be linearly independent. If, sorry for going all the way back here, you guys. These two vectors were the vectors I needed to form a basis. Let's say I only had one of these, right? Then this would not span the entire subspace generated by the two of them. That was part A, right? I don't have enough vectors to match up with my bases that I need. Right? If the number of vectors I have is less than the number of basis vectors, I'm not going to be able to span the space that I'm trying to span. Okay, so that's an example of A and B from our previous example, and that's it. So again, you guys, I know that this was very abstract. I try to be very, very intentional in my wording for a lot of stuff. I definitely suggest that you go through and probably watch this video again, which is not too bad because it's half the length of a normal video. Try not to repeat myself too many times like I do normally. But again, this is a very, very abstract section, a very abstract chapter. So if you need to rewatch it, don't feel bad about it, okay? See you guys on the next video. The next video should be relatively short because we covered a lot of stuff that is in the next video, actually in this video.